Hey everyone, welcome to this lecture. In this lecture, we're going to talk about angular kinematics of human motion. It would be good to kind of review some of the linear things because we'll bring some of the terms back that we've talked about before. And it's related to linear motion in kinematics, linear kinematics. We just start to use kind of angles. We'll go ahead and get started. So you can pause the video here and just think about this. Again, if we were in class, we would think pair share, but you can simply just kind of talk about um, your technology paper with someone or kind of think about it in your head. You should be working on that. Quick overview, understanding angular motion. Remember, the body consists of a bunch of segments, is really how we look at the body, each kind of body segment that are all connected through joints. And almost all of the motions that we utilize in the human body um, involve rotation around some kind of axis around those joints. Um, so pretty much angular motion is present in all aspects of our lives. And so we tend to think of things being more linear motion when we think about like walking kind of in a straight line. But to get there, we have to use kind of angular motion across our body. Angular motion is the same as linear. It's just in an angular sense would be kind of a way to kind of look at that. We'll go ahead and jump in it. So when we look at angular kinematics, again, it does have this kind of relationship to linear kinematics, but again, it starts to talk about angles or degrees. With this movement here, we'll use the curl, the motion of a curl, so raising the arm up, doing that curl position a lot today. What you see is that there is a linear motion to some extent, or we can look at a linear displacement. So the wrist moves from point A to point, it's A again, but the distance, so dA right here is that distance that was moved. So that's a linear displacement from beginning to end. However, if you actually were to track it, it more follows this kind of curved line because it's rotating around an axis. And so our wrist doesn't move in a straight line, it's more kind of curved in this way. And so that's that angular movement. That angular movement is more going to be measured in degrees of how many degrees were we from start to end. And so we'll kind of look at that as we move forward. But you can kind of see how they're very related. It's just kind of looking at a distance versus kind of angles or degrees is more how they're measured. And there's also radians and other things we can look at as well. And so you can start to see how that becomes more useful when we're talking about maybe a diver spinning around one or two times, which you see here. Go back one. So here you can actually click on this video and talk about angular velocity from sports science. These guys are really great. I would encourage you to go get that PowerPoint and watch this YouTube video, or simply Google sports science inside the quad flip. These guys are really good about breaking things down in biomechanist, exercise physiologists. They're really a good show. I don't want to waste your time watching it here, so just go ahead and pause the video, go find this and watch it, and then jump back into this video. So when it comes to measuring angles, okay, and measuring kind of this, where we can start putting values around this angular motion, we typically use at the most basic feature of what's called a goniometer to measure joint angles, okay? These are still used today. They're very basic. They're the hand tool that was first designed. And more complex things, we get into video analysis that can measure these things and putting markers on people, but this is still useful. And so you can see one in the picture here. And so it has two arms on it. Those arms can be adjusted depending on the model to give you the right length if you're trying to measure to a particular joint. And then in the center, you can see that it's marked with degrees. And this moves very freely. So you kind of put it up against, you match the rotation here, the point axis of rotation here with the joint you're looking at. And you kind of set it on there and match these up with the segment length. So in this case, the forearm and kind of our upper arm here, the humerus. And then you can move it freely as the person moves. And when they stop, you can see how many degrees or what angle was moved. So when you're measuring those angles, joint angles are always measured as segmental movement. So you're measuring the angle a particular segment moved. So again, it could be the forearm compared to the humerus. If you're looking at the shoulder, it's going to be the humerus compared um, to our kind of shoulder here. And so we're looking at just a particular segment of movement each time. And we're always comparing that to that anatomical position. So remember that anatomical position, standing straight up, arms down by your side, thumbs out. So we're always measuring in reference to that. And so the straight fully extended position is always considered the 0 degree mark, and then we kind of move from there for each body segment that you're looking at. So when we're measuring this, we may also want to look at what is called angular displacement. And so remember that displacement is simply the change in an angle position or orientation of a line segment. Okay, and so displacement is how far we moved at in that angular position. It's assessed as the difference in the initial to the final angular position of a moving body. So it's from beginning to end. It doesn't matter what happens in between. It's just our starting point to our ending point. Um, and so if we make a vector in that, that's equivalent to an angular distance. Okay. And so typically when we're talking about angular displacement, we typically talk about it in degrees. So the body segment moved 10 degrees, 90 degrees, 180 degrees. We can also use radians. So radians, if you remember back to trigonometry, you've moved like pi or 2 pi or various things like that. So, half pi. Radians are used, but you tend to not hear them talked about as commonly. And then we also have revolutions. So if we're moving more, it could be it had 1 revolution or 2 full revolutions or 2.5 revolutions or whatever we're kind of looking at there. And so again, when you're looking at that angular displacement, again, using that curl because it tends to work out well, the if we look at a curl, so you start in the downward position, so kind of like here, and you move up, and then you move back down. So the final placement was actually the same as the beginning placement. The angular displacement was 0. There was no actual displacement from beginning to end. However, if you take your arm from the starting position and you start down and then you finish in the upward position, such as this, we can look at that angular displacement from start to end position. And so that's really important for us to remember is that angular displacement can be 0 if we return to the same position. So if you do 1 full revolution and you stop in the same spot, that is technically an angular displacement of 0 degrees, but it would be an angular displacement of 1 full rotation. So you can see where units can start to matter. So again, continuing on this, if we look at A, so we can see that the ball starts in the most left position, swings all the way to the right position, and then finishes kind of in this center position without the dotted lines. Okay, and so what you can see is you can see how the ball traveled. Okay, we can see that total traveled distance of the ball, and so when we're looking at it, we can see the path of that pendulum motion. But there are two different things we can look at. When we talk about angular displacement, again, angular displacement is this black line here that is just simply the start to the end. Okay, that's how many degrees we would say that moves. However, if we wanted to talk about angular travel, okay, or we wanted to look at angular distance traveled, we would then have to measure the angle between from the initial all the way to the furthest right position, and then this little distance traveled between the furthest right and its final resting position. Now, you may be asking yourself, would it matter that these are in different locations, right? So we're looking at angular displacement here and then angular distance here. Well, when it comes to angles, it doesn't matter how far away we are from the center of axis. The angular displacement is the same. So 1 degree out here at my mouse where the ball is the same as 1 degree here. Now, what does change would be the linear distance traveled, and we'll get into that a little bit later. So when it comes to angular displacement and angular distance, we also can talk about angular velocity. And so this is the rate of change of the angle position or the orientation of the line segment. So if you think about velocity like running in a straight line, like how fast you're running, how fast are you moving, angular velocity is just talking about an angle. So how quickly are you changing your angle? Is it 1 degree every second? Is it 2 degrees every second? So on and so forth. So angular velocity is equal to angular displacement divided by the change in time. So if we know the total angular displacement that occurred and we know how long that took, we can find angular velocity. And again, that's usually in degrees per second, sometimes radians per second, but we can also get into revolutions per minute. And so you guys may have heard of RPMs for certain things in like an engine. And so this is talking about how many times it goes around in a single minute. And this is talking about an angular velocity. So very related to that, of course, is angular acceleration, and this is simply the rate of change in angular velocity. So angular acceleration is equal to the change in angular velocity divided by the change in time. Again, going back to the same things we talked about, just now with angles instead of linear displacement. So the reason it's important to kind of look at this and start to talk about some of this angular acceleration and velocity is we start getting into the resistance of change. So we talked about Newton's laws before, and so in angle, especially in angular acceleration and velocities and deceleration, it starts to play kind of a bigger role because we're around this axis. And so if we look at bat A and bat B, what we've done is we've placed a weight on these bats. And so I always think with a bat, the axis of rotation is going to be near the handle, so kind of towards the letter section, and then the other end is going to be kind of what's moving. And so in A, we've placed the weight further down, further away from the angle of rotation, and B, the weight is closer to the angle of rotation. The mass of each bat is exactly the same, but if you tried to swing the bat, A and B, you would notice that it's much harder to swing bat A than it is bat B. It's also harder to stop bat A as it is opposed to bat B. Um, and that is because of the distance that it is placed away from the axis of rotation. The further we are away from the axis of rotation, the more that can affect our angular acceleration and deceleration due to that momentum. And so here we can look at clicked on accident. There's a video here to talk about torque and moment and inertia. So a lot of that has to do with the inertia that we have and the way this looks at a golf ball. And so really take a look at this because it really starts putting that picture in nicely about what we just talked about with the bat and the weight placement and angular acceleration and velocity and inertia. Really puts a good picture on that. So just pause the video, find that one. Again, you can search it by the name, download the PowerPoint and click play, and then resume this video once you are done. So when it comes to angular acceleration, resistance does play a big role. And so realize that when it comes to human body movements, different angles of other joints related to the one that we are moving can make a big difference. So if we see here, someone has a straight leg versus someone having a bent leg at the knee, and so the knee angle when we're moving our hip affects the moment of inertia. Okay, the body's tendency to resist angular acceleration. Okay, so when our knee is bent upwards, like in the first picture, it is much easier for us to resist angular acceleration because all the weight is much closer to the axis. Okay, the rotational axis. When it is further away, we tend to we struggle more. It takes more effort to resist this angular acceleration once it's started, or even to produce it. And so, when we're looking at this, we see this change. Okay, and so where we want to look at this is kind of in running. So during sprinting, extreme flexion. Okay, so think about flexion at the knee reduces the momentum inertia of the swinging leg. And so what you'll see is that runners will start to not over necessarily, but they're going to have extreme knee flexion. They're going to bring their foot way further back while they're full sprinting than when they do on a regular jog. And the reason for this is their foot is moving faster. And so as they bring that foot up, it's allowing that weight to be closer to the hip, and so easier to change the acceleration and the velocity of the hip. Okay, so we're trying to get the leg back forward, and so bring that up pulls the mass up, like we saw in the last picture. Okay, and so when all the weight is closer to the center of rotation, we're able to effectively get this leg moving forward faster. Okay. And so then as we are kind of getting past that halfway, you'll see the leg kind of extend outward, straightening up, and that's going to actually increase the acceleration, moving the foot itself faster to take a longer step. And then we keep that leg straight coming back because we don't want to lose that propelling forward. Okay, so the body is really good about using this moment of inertia to kind of shorten the leg so that we can get it forward faster. But then we keep that leg extended through to transfer power, but also to keep our momentum moving forward in a linear direction. So, kind of think about that for a second. It's a lot to kind of digest. So, when we talk about angular momentum, which we've kind of been looking at, so angular momentum is the quantity of angular motion possessed by a body. Okay, it's how much of that is coming in, and so it's usually measured as the product of the moment of inertia and the angular velocity. Okay, as mass or angular velocity increases, angular momentum increases proportionally. So, what we're saying is that it doesn't matter if your mass increases or your velocity increases, it's going to increase your momentum. Okay, your momentum. Okay, at the same kind of rate. And if we decrease it, it's the same as well. So, a factor that influences angular momentum is the distribution of mass with its respect to the axis. So again, what we've been talking about this whole time is the fact that if we put heavier weight further away from the center of axis, that angular momentum is going to be increased once we start moving it. Okay. And so again, think about swinging that bat with the heavy object on the end. It's really hard to get started, but once it does start, it's really hard to stop. And so this plays a role in our movement. So the reason that can make a difference is things such as figure skating is another example here. So again, pause this. It's going to talk about angular momentum, physics, and things like that. Pause that. It's going to relate that back to some ice skating. And then once you're done watching that video, simply come on back and we will continue to talk in our lecture. So angular momentum. So again, think about swinging that leg and how we kind of extend to help us kick that ball. Again, relating back to the video you just watched, and those different distances of how we start closer here, but then as we kind of go to kick that ball, we extend the leg out. This becomes longer, greater distance, and so that momentum helps keep it going to kick that ball further and faster. So, what's the principle of conservation of angular momentum? Well, when gravity is the only acting external force, angular momentum is fully conserved. Total angular momentum of a given system remains constant in the absence of external torques. So, really, it's like the laws we've talked about. Unless there's something acting on it, it's going to stay at a pretty constant rate. Unless we kind of do things that are going to add torque to the system. And so with that, we have this, and so you can see they're kind of tucking and rolling to do this dive. So with angular momentum being conserved, changes in the body configuration produce a trade-off between the moment of inertia and the angular velocity. So again, we have this moment of inertia and the angular velocity, and so it's trying to stay pretty constant. And so what happens is when we bring the weight in, so as the person kind of tucks themselves into the ball in this example, what happens is we start to bring the weight closer, so the angular momentum or the moment of inertia is trying to stay similar, and to do that, what happens is we start to spin faster. So there's an angular velocity that tends to increase, and then once we kind of straighten back out, the angular velocity decreases to again maintain that inertia. So again, it's kind of resisting that change when the weight is further out. So when we talk about this kind of angular momentum in another aspect, so such as a volleyball spike, during the airborne execution of volleyball spike, what you see is compensatory rotation in the lower extremities. So you're swinging really hard forward on that ball, and that's wanting to rotate you around an axis. And so what you see is your feet kind of kicking back or coming up to try to offset. Sorry, coming up and then kicking out. of that offset, that angular momentum. And so what you can see is here when you spike the volleyball, the angle wants to pull you forward and then kind of down towards the ground face first, and then your feet kicking out kind of straighten you back up. And so this is to conserve that angular momentum. It's keeping it the same, but we're offsetting it so that you don't face plant. Your body does this very naturally. You don't want to hit your face. So again, here, the way we can use this to our advantage is through arm swings. So during a takeoff of a dive, the arm swing actually helps add some of this angular momentum to help the rotation going forward. And so these are very important factors that, again, we do unconsciously. All of us kind of are aware of these things, and we're not sure necessarily why we do them, but there is mathematical and physical principles that kind of go with them. And then once you kind of know them, you can take even more advantage of them. So bigger arm movements, more efficient arm movements to get that moving. So when we look at this, we tend to kind of put them into different categories, but yet when we with angular motion and linear motion, but tends to be the things we do kind of incorporate both. And so the relationship between linear and angular displacement is that the greater the radius is between the point of rotation and the axis of rotation, the greater the linear distance traveled. So, for example, if I have a short bat per se, so or if I just use my arm, let's say I just use my arm fully extended to kind of swing, just like I do a bat. Well, if I use the same angular velocity, okay, so I swing at the same pace, what you would notice is your arm's going to move a certain distance over a certain amount of time, okay? However, if I put a bat in my hand that's longer, so I get further away, over that same amount of time, that bat actually is going to move a greater distance even at the same velocity, and that's because it's further away from the rotation of axis, right? Um, and so this is really important to know that we can get some advantages and disadvantages. We can greatly increase the actual linear speed of something by just simply putting it further away from the center, the axis of rotation. But it's going to take greater force to kind of speed that up because think about the inertia we were just talking about. So the greater the angular velocity of a baseball bat, which we just kind of talked about, the further the struck ball will travel if everything else is held similar, okay? And that's because that end of that bat is swinging, moving a greater displacement, moving at a greater distance over time at a faster velocity, and so it's going to hit the ball further. So think about a long jump, okay? So with a long jump, you have contributions of the arms, but you also have contribution of the legs. And so which one plays a role? And so think about that with kind of the long jump as well. How much are we contributing with arms? How much are we contributing with legs? And how is that kind of helping us as we go for that long jump? And I believe this should work as a video. My computer is kind of freezing at the moment, so we'll see if it... Oh, good. Well, I guess we're going to restart, and you guys get to sit here and watch this restart real quick. I'm going to pause the video and jump back into it when it completes. All right, so PowerPoint has fully crashed, but I can still shoot this video. The last two slides of the lecture were simply, this is a video that you can download the PowerPoint and watch. Then we ask you about diving to look at that video and to look at the contribution of arms and legs. Again, trying to put all these into motion. And then the very last slide of your PowerPoint just simply asks you to practice a few things so that you can kind of get a feel for how much these things play a role. So I'll list them off in case you don't have readily access to PowerPoints, but you can always go and look at those as well. So just a couple of things to practice so you can see this is do a standing broad jump. So do a horizontal jump without using your arms, okay? So jump and don't use your arms at all. Notice the distance of that jump. Then I want you to do that again, but this time use your arms. Okay, use your arms to do that broad jump, that horizontal jump. Note the distance that you jumped. Which one of those helped you to jump further, and why is this? Like, what contributed to that further jumping? So then we're going to go, instead of jumping horizontally, we're going to go jumping vertically. So jump as high as possible with both of your hands held above your head. Note how high you kind of jumped. So again, hold your arms above your head and try to jump. Next, stand next to a wall and jump as high as possible, holding both hands against your chest. Okay. Um, and then reach with one hand upward as you jump. So you're going to stand next to a wall, both hands at your chest. You're going to jump, and then as you come up, kind of reach with one arm. And then try that exact same thing with throwing both arms in the air. And on both of those, note how high you jumped. And then finally, do a step up jump, step into a jump. So take one step and jump and simultaneously throw both of your hands upward at the same time, and note the height of your jump as well. So on those those four jumpings that you did, which one of those methods resulted in the highest jump? And why do you think that is? What played a factor in that? So that concludes this PowerPoint. If you guys have any questions, please shoot me an email. Other than that, we will talk with you guys in a little while. But just let me know if you have any questions on angular kinematics. You guys have a wonderful day.